right, hello everybody. Welcome to the second oral session of the Organic Geochemical Tools to Understand Life, Climate, and Environments Through Time. Today we're going to focus a bit more on the through time aspect. Hope you guys enjoyed the talks yesterday and the posters yesterday evening. My name is Jordan Hemingway. I'm convening here with Lina Perez Angel, who's over there. And our first talk today is actually another award medal talk. And so if you learn anything from this, it's that if you want to get a medal in your career, you should study organic geochemistry. And so we have a talk by Shucheng on organic records of progressive ecosystem collapse leading to the largest biotic crisis in the Phanerozoic. But I think first we have a brief introduction to the award.
Good morning. It is my pleasure as the chair of the Organic Geochemistry Division of the Geochemical Society to introduce the 2023 Alfred Treibs Award. The Treibs Award is given for major achievements over a period of years in organic geochemistry. The award is named for Alfred Treibs, whose contributions to the discovery of geoporphyrins and elucidation of their structures confirmed that these structures were derived from chlorophyll. And in doing so, he confirmed the biogenicity of petroleum, and in doing so, opened up the study of biomarkers for paleo-environmental studies, biomarker applications to both modern and ancient environments. And in a sense, he is the father of our field, and so it is a great honor to receive this award as an organic geochemist. This year, we recognize the accomplishments of Professor Shucheng with the Treibs Medal. Unfortunately, at the moment, the citationist has not yet made it to the convention center, so we're going to start first off with Professor Shia's medal lecture, and then hopefully afterwards we can find Tom Algeo, who can detail the enormous accomplishments that have brought Professor Shia to this point in his career. So please come up.
Okay, thank you, Chris. So I have to go to give my lecture first. So today I will go to talk about the largest biotic crisis in Phanerozoic, which occurred across Permian-Triassic boundary. I will show the progressive ecosystem collapse on the basis of the organic geochemical records from both marine and terrestrial sediments in South China. This study is in cooperation with Tom Algeo, Paul Wagner, Gordon Love, Jia Wu, and Kim Lo. Here shows the changes of biodiversity for the past 600 million years. The sharp drop here across the Permian-Triassic boundary is the most severe mass extinction about 252 million years ago in Earth's history. Lots of scientists conduct investigations on this biotic crisis event. And here I'm going to show the importance of organic geochemistry records to deserve the biotic crisis issues. There are lots of issues, but one of the critical issues is the pattern of the mass extinction. Most scholars hold the point of view of one abrupt crisis which is known as the end-Permian mass extinction. In contrast, some scholars, including some colleagues in my group, insist that multiple episodes of the mass extinction. This is known as the Permian-Triassic mass extinction. Here shows the stratigraphic distribution of over 300 species from Shucheng SSP section in South China. Both one abroad classes and multiple episodes were discussed in this single section. The debated point is the presence of the second episode here indicated by the red arrow in the early Triassic. A compilation of 7 sections in South China did demonstrate the presence of 2 episodes of the mass extinction here and here. Of importance is the calculation of the extinction rate indicate the second episode in early Triassic is much greater than the first episode for the extinction rate. So this study not only demonstrates the presence of 2 episodes of the mass extinction, but also raises the question why the second episode is suffered from more severe conditions than the first episode, and what are the causes. Further study on these 7 sections in South China led to some more important findings. While the mass extinction took place as a pattern of 2 episodes, as shown here by the biodiversity job, the well-known replacement of the Paleozoic faunal ecosystem by the modern faunal ecosystem occurred at the second episode in early Triassic, rather than the first episode here. So this change is the well-known shift of marine faunal ecosystem, and also called the featured by the physiological biotic. So here again it shows the more severe environmental condition during the second episode. So from the overview of the previous study, we could know some critical issues left to be resolved. They include whether the mass extinction is featured by the 2 episodes of crisis in marine settings. If yes, how is the land ecosystem? And then why is the second episode suffered from more severe environmental conditions? So here I work on the organic geochemical records from both marine and terrestrial settings. These data clearly indicate progressive processes. So this is a Permian-Triassic crisis rather than the end-Permian crisis. As early as 2005, we conducted the investigations of organic geochemistry on the Shucheng SSP section, and we could, for the first time, identify 2 episodes of the nitrogen fixation bacterial expansion, as shown here and here. The 2 microbial expansion were documented to follow immediately after the 2 horizons of mass extinction, here and here. So the microbial lipid records from Shucheng section indicate at least 2 episodes of the deterioration of the environmental conditions, such as anoxia. However, the interval to cover the 2 episodes of biotic crisis is concentrated in the very condensed strata, which is less than 20 centimeters in thickness. So this is very difficult for us to establish the high resolution event sequence. So we expanded our work to the South section in South China. This is the paleogeography of South China. This is South section, and this is Mission section I just talked earlier. Both the South section and the Mission section are the deep water phases, but South section is a bit deeper than the Mission section, as I show here. South section, Mission section, and then this is the water depths. The most important thing in South section is the interval to cover the 2 episodes identified in the 20 centimeters of Mission section is very expanded here, which is about 5 meters here. So we conducted organic chemistry investigation on the South section, and here is the date. I show here the profile of microbial lipid records related to sulfur cycle, nitrogen cycle, and carbon cycle. And we could see here for a period of 20 million years. And we could see here some parameters show a progressive increase like this one to the Permian-Triassic boundary. So with the maximum found at the horizon of biotic crisis. So we try to show the molecular and isotope profile, just concentrate on the very short interval across the Permian-Triassic boundary. This is Permian-Triassic boundary, and we could identify here the change of 2 episodes, which denoted by different colors: yellow color for the first episode, or blue color for the first episode, yellow color for the second episode. And we could first find here that some parameters, such as the oceanic stratification, the nitrification, are also much greater during the second episode than the first episode. Furthermore, the biomarker for the green sulfur bacteria indicate of the folding zone Yersinia were only detected during the second episode, rather than the first episode. So these microlipids from South section also tell us the oceanic condition could be much worse during the second episode. So this probably explain the high extinction rate and the faunal extinction as I showed earlier. We first compiled the green sulfur bacteria biomarkers from sections with different water depths. They include the Bora section in Italy, Peace River Basin in Canada, and the South section in China. And we could see here that the biomarker of green sulfur bacteria were not detected in the shallowish Bora section, but present in the relative deep section of Canada, and then show the maximum in abundance. Here is the number. So this the maximum in abundance in the deepest South section. So this special temporal affiliation of the green sulfur bacteria biomarker indicate the folding zone Yersinia expanded from shallow water to deep water, as I showed here in this figure. These microbial records indicate the more deteriorated environmental conditions during the second episode are consistent with some other geochemical data. For example, I show here the boron isotope data, and this also indicates the oceanic acidification occurred during the second episode rather than the first episode. So now we can compare the oceanic condition between the 2 episodes. The oceanic acidification, folding zone Yersinia, oceanic stratification, nitrogen fixation, and anosmic condition are all shown to be much stronger during the second episode rather than the first episode. So these microbial lipid records, together with some other geochemical data, tell us the much worse environmental condition during the second episode. So, and this explains the more severe biotic crisis at the second episode of early Triassic. But why the second episode is featured by the more worse environmental condition? What are the causes? Here I show the profile of the temperature calculated on the basis of isotope data of apatite from compounds from different sections in South China. This is South section, Meishan section, and some other sections. And we could see here that the temperature rise keep going after the first episode. So the temperature is much greater during the second episode than the first episode. So now, on the basis of organic geochemical records and some other geochemical data, we can establish the event sequence for the second episode. The temperature rise will cause the enhanced ocean stratification, and which result in the anosmic condition and then the nitrogen fixation. And then the anosmic condition, as well as the abundant CO2 concentrates, will cause the oceanic acidification and Phanerozoic erosion. These deteriorated environmental condition will finally cause the faunal mass extinction and then the shift of the faunal ecosystem during the second episode in early Triassic. Here is the summary of some important events for the two episodes identified in South China. They include biodiversity here, sea surface temperature here, delta 13C, nitrogen fixation, Phanerozoic erosion, oceanic acidification, and soil erosion. And we could see here some events were all present during the second episode in early Triassic, also the maximum or the minimum during the second episode rather than the first episode. So these data indicate this is a Permian-Triassic crisis rather than the end-Permian crisis. All these records I showed earlier are from the marine section, and then the marine records can first tell us about the changes of the land ecosystem. Here is the abundance of monotyne relative to hoppings. Its affiliation also shows a pattern of two episodes, this one and then this one. The large affiliation in such short interval cannot be explained by the changes of organic material. So we proposed this could be the process of the land import. This process was later confirmed by some other scientists. And the ratio of monotyne to hoppings also indicate much greater value here during the second episode, which is related to the land ecosystem. So these records may also indicate the progressive process in land settings. So yes, this would be true. So we try to collect samples from a drilling core of terrestrial sediments in glacial platform in South China. This is the site. This is the drilling site, and to the east of the drilling site is the well-known marine sediments of South China. South section, Meishan section, as I taught earlier. We collect the mudstone from the drilling core to conduct analysis of organic chemistry. And here is some data from the drilling core. And we could identify the change of some parameters, show 3 distinct intervals denoted by different colors, here, here, and here. The black blobs shown here in the result column are the cold beds. And we could see here the 2 parameters began to decrease at this horizon, which is well before the disappearance of the cold beds. This is the abundance of C29 stenos, and this is the Pleistogen to Phyton. So the 2 parameters, the decrease of the 2 parameters indicate the decrease of land settings. So it is appear that before the disappearance of the cold beds and then the decrease of biodiversity at this horizon, the terrestrial biomass began to decrease first. So this is the very early stage of the biotic crisis. Such an initial crisis were also documented in marine sediments. As I show from Mission section, this is known as the lipid effect, which shows the body size of some species show a sharp decrease here before the biodiversity drop. So this is also an initial crisis in marine sediments as documented at the Mission section. I will show here more profile from the drilling core, which enable us to identify the high resolution event sequence. Follow this initial crisis, as I talked earlier, are the sharp increase for these parameters. This is the abundance of faunal, which is related to the soil erosion, and the sharp increase indicate the collapse of the terrestrial system here, just at this horizon, which is consistent with the biodiversity drop. We could also note here that the increase of these parameters show a pattern of 2 episodes. The first episode here is associated with the high abundance of charcoal. This indicates that this is the wildfire-induced change, and then the second episode is associated with the high abundance of metals, including mercury, copper. So the second episode is induced by the volcanism. Anyway, the data from the drilling core indicate the progressive collapse of terrestrial system, just as we observed in marine settings. Just in this drilling core, the impact of metals from volcanism were documented to play a very important impact on the vegetation. This is shown by the presence of the teratological sporomorph. These teratological sporomorphs were only identified in high abundance here during the second episode, rather than the first episode. So this again indicated the more severe conditions during the second episode in terrestrial settings. So both the marine and the terrestrial settings appear to show the comparable 3 stages of variation. They began with an initial crisis here and here, which is known as the lipid effect in marine settings, or as the decrease in biomass in land ecosystem. This initial crisis is followed by 2 episodes of decrease in biodiversity, with the second episode being more severe conditions. In marine, the second episode is featured by the physiological text shift, and on land, the second episode is featured by the mutagenesis in plant spores. Also, it is very difficult to make a high-resolution stratigraphic correlation between marine and terrestrial settings. These organic chemical records indicate marine settings and terrestrial settings are suffered from comparable 3 stages of biotic crisis, which finally led to the largest biotic crisis. So here is my conclusions. Lipid biomarkers can be used to serve as powerful tools for ancient environmental study. They work for a variety of sediments, including both marine and terrestrial settings. Lipid biomarkers show comparable progressive ecosystem collapse in marine and land of South China. There is an initial crisis without any biodiversity decrease, but featured by the decrease in biomass of land or the body size of some species in marine settings. And the second episode in early Triassic is featured by more severe conditions than the first episode in Permian. And so this is a Permian-Triassic crisis rather than Permian crisis. And here is the acknowledgement. And as NSF of China, Ministry of Science and Technology of China, for funding BGG Static Laboratory for access to the analytical facility. And we have long-term collaboration with Organic Chemical Unit of Bristol, in particular, Professor Richard Evshed, and also to all my colleagues and PhD students. Thank you.
Thank you so much for the talks. Any questions online or in person? Great.
Thank you very much for that great talk. I was just wondering, do you want to speculate what was driving this two-step mechanism? Was this all volcanism in 2 steps, or like what was driving this major crisis that can happen in 2 steps?
Yeah, it's a good question. Well, we guess the climate change, in particular the temperature, may be one of the most important drive to this variation I just talked about. As I showed earlier, the temperature is much greater during the second episode than the first episode. Also, we may also first think why the temperature changes so much in 2 steps. Different people have a different point of view. Most people hold the point of view that the volcanism responds for the temperature rise from the end Permian to early Triassic. Thank you.
Hi, nice talk. Just a question about your mercury proxy. It looks that you have first wildfire and after a mercury peak. Are you sure that this mercury is not coming from all this organic matter which can be reworked? And did you run some mercury isotopes in order to more or less rely this to some volcanic activity?
You mean the organic come from some other straight?
Yeah, your peak in mercury is post-dating the wildfire, okay? So it means that maybe part of this mercury could be recycled from organic matter, which is scavenging normally mercury. Did you try to measure stable isotopes of mercury isotopes in order to check if really mercury is from volcanic origin or from soils which has been reworked?
This is a good question. We did measure some isotope analysis on this section, and not only the organic chemistry records, but also some other paleontology data, including the palynology data, indicate that they cannot be derived from the local sediments or local organic matter. Thank you.
We have more questions in the audience or online. I can ask a question or two. Super interesting talk, thank you. I was wondering, and you briefly mentioned this, the age constraints between the marine and the terrestrial cores. So if I saw the axes right, the difference between the 2 episodes or 3 episodes was about 50,000 years, is that right?
Sorry, I cannot get your point.
I'm wondering basically how well constrained the age dates are between the terrestrial and the marine cores, and if you can really align the first episode versus the second episode in both of those settings.
You mean the 2 episodes are the signal of local rather than the regional or global?
I mean, I guess my question is really just how well do you know the ages?
We conduct some other sections around 30s, in addition to such as the Polak section. We also found 2 episodes of the microbial expansion, so they all indicate the 2 episodes exist around the Tethys region. And also we have carbon isotope composition from the world, and they all show the 2 episodes of negative shift in carbon isotope composition. So all these data indicate the 2 episodes are global, not local signal. Thank you.
And you're confident with the ages in saying that the first episode is the correlative in every section, or? It's okay.
Or maybe another way to ask that is, how do you constrain the terrestrial records that you use? How do you do the age control on those ones?
How? Sorry.
The dating, the age constraint in the terrestrial records.
The aging. No.
That's okay.
Sorry.
You have any more questions? Because of the fact that the person who is supposed to introduce can't be here until the end of the session, I believe, we have plenty of time for questions because we want to stay on track for the rest of the session. So I can ask more. I'm curious if you did any stable isotope measurements on your hopanes. So you showed some 2-methyl-hopane ratios. I'm curious if you did C13 measurements on those.
Yeah. We measure some isotope data on the hopanes or monitors, and they show different values. For the monitors is a bit enriched than the hope compounds. So this indicated the monitoring derived from terrestrial sediments. So we proposed this to be applied to the terrestrial input.
The 2-methyl-hopanes is a terrestrial input. Is that what you're saying?
Sorry?
The 2-methyl-hopanes from the C13?
2 major hopanes.
Yeah, you showed at one point a 2-methyl-hopane ratio and saying it increased, meaning more diazotrophy and nitrogen fixation. I'm just curious if there was some isotope data on those biomarkers as well.
You mean for the Hopins?
The Hopins, yeah, the Hopins.
No.
No isotope.
No.
Okay.
No.
Okay.
I can ask another question. I was wondering, in the episodes that show intense soil erosion, do you have any other proxy, like clays or other minerals that also show that intense erosion in those sections?
And no, sorry, I didn't get your point.
I think it was episode 2 and 3. They show at the end that show soil erosion, like an intense erosion. No?
You mean the ask process for the enhanced whistling for the second episode?
Yes, say the enhanced erosion, yes. Yes. Do you have, besides the biomarkers, another more sedimentological proxy that also shows the erosion, the high intense erosion shift?
Yeah. In addition, the ratio of molybdenum to Hopins, we also some geochemical data such as CRA indicate the enhanced whistling on the land. So they are considered between the inorganic geochemical data and then the organic geochemical data. Thank you.
Hello, thanks for the great talk. And I think this PT transaction is very clear in your sections, and it's very distinct to the 2 episodes with so many evidence. So it's some contradictions in these land and ocean records. So in the land records, in the Mesan section, you'll see two episodes. But in the ocean section, they saw 3 episodes. I'm surprised to see that the volcanics indicated by mercury is in the 2nd episode. I know this is probably not your work, but to your knowledge, will this volcanism also being recorded in the ocean sediment? That refers to the previous question about the age control. If the 2 volcanisms in the land ecosystem and the ocean system pairs with each other, then we can have a better edge control. Thank you.
Yeah, thank you. I emphasize the presence of 2 episodes related to the decrease of biodiversity, but they also an initial crisis before the decrease of biodiversity. This initial crisis can be identified on both marine and land sections. So if we include the initial crisis and then 2 episodes of biodiversity crisis, there are 3 stages of changes. So both the marine and land section are consistent. As to the volcanism, there are some different records in South China, and in the South section, we only identified the places of volcanism by the mercury during the 2nd episode. But in marine section, as you told, we also identified the volcanic edge during the first episode. So the volcanism in South China might play important roles for the 2 episodes, like in the second episode. Thank you.
Great, thanks. And actually, we can do our formal introduction to the medalists
Okay,
now.
thank you. Thank you.
Kind of out of order, but I'm glad we can get it done in the end. So let's thank our medalists one more time.
Okay, do we have the slides for the?
Is it this one?
Yes, that one. Very good. Okay.
Here you go.
Very good. Okay. I'd like to apologize to Professor Xie, to the Geochemical Society, and to the Goldschmidt Conference attendees for being late this morning. I confused the time of the session. We're here today to honor Professor Shucheng Xie, who is a professor at the China University of Geosciences and an academician of the Chinese Academy of Sciences. He's being honored today with one of the Society's highest awards, the Alfred E. Treibs Medal. I've collaborated with Professor Xie for many years, and in the course of those contacts, I've come to know him as a world-class scientist who's made many outstanding contributions in the fields of organic geochemistry and biogeochemistry. Professor Xie's research has greatly enhanced our understanding of the role of microbial communities and microbially mediated processes during major events in Earth history. He has worked to decipher the relationships of microbial communities to changes in biogeochemical cycles, including those of carbon, nitrogen, and sulfur. Professor Xie has been a leader in the development and application of biomarkers, such as the Moritane proxy for terrestrial organic inputs and the 2-methylhopane proxy in combination with nitrogen isotopes for nitrogen-fixing cyanobacterial inputs. He has applied these tools to many geo-events, including the major events of the Ordovician-Silurian, Fronian-Fumenian, Permian-Triassic, and Triassic-Jurassic boundaries. He's done this in collaboration with many students and colleagues in many papers over the course of his career. Professor Xie has made outstanding advances in the field of microbial GTGTs, one of the most widely used biomarkers in paleoclimate research today. Among other contributions, he's proposed the RIB index as a tracer of aridity, and he discovered that temperature and hydrology have differential effects on the C6 and C5 methylated bacterial GTGTs that can be quantified using the IR6ME index. These proxies, which have greatly contributed and enhanced our knowledge of paleoclimate, have now widely used. Professor Xie's work has furthered our understanding of the application of lipid biomarker proxies to various types of paleoclimate archives, including speleothems, loess paleosols, and soil peat deposits. His work on GDGTs, 3-hydroxyl fatty acids, and other lipids and stalactites was groundbreaking in recovering biomarkers from such relatively organic poor archives that permitted analysis of a range of environmental parameters, including temperature and pH. He has also helped to pioneer the use of deuterium isotopes of sedimentary lipid biomarkers as a paleoclimate proxy. Applying these and other proxies, Professor Xie's research has led to important insights into the operation of the East Asian monsoon, its impact on carbon cycling in Chinese peatlands, and changes in the dominant mode of summer rainfall variability over East Asia, all of which represent key research contributions to our understanding of the long-term evolution of the East Asian monsoon. His findings have appeared in notable journals, including Science, Nature, and Geology. I would be remiss if I did not note his significant contributions to the development of geobiology as a field of study. He's accomplished this through organization of many meetings and theme sessions on geobiology, training of many graduate students in this field, and serving on the editorial boards of geobiology and other topically relevant journals. Professor Xie has also been instrumental in laying the foundation for a new field of study, geovirology, the study of viruses and their roles in Earth history. In conclusion, I would like to note that Professor Xie is a fitting recipient of this award, not only because of his research and professional leadership accomplishments, but also for the manner in which he emulates the positive character traits of Dr. Alfred Treibs, a scientist known for his modesty and civility in interacting with fellow scientists, students, and the public. Professor Xie thus honors the memory of Dr. Treibs in being a true gentleman scholar. Thank you.